Good morning, Physics 2. Today we will be talking about the buoyant force. Now, the buoyant force is based upon the density of liquid, which as we know is mass over volume. The buoyant force can be calculated by taking the volume of the liquid displaced times its density times gravity. Or, to simplify it a little bit, you can take the mass of the fluid displaced times gravity to get the amount of force exerted upon your object in newtons. Now, the buoyant force works upon the principle that when you place an object in water, it displaces the liquid. And then that water will then apply an opposite force equal to the displacement of liquid. So in this, we have a beaker. But when we place a small toy boat in that same beaker, it A, floats because it is lighter than the amount of force that the buoyant force acts upon it, as well as we see the water level is higher because there is that displacement of water. Now let's look at some examples. And we're back. So, in our first example here, we have a hollow metal ball, and we're putting it into a bucket of water. When we put it into the bucket of water, we see that the volume increases by 2.5 liters. Now what we want to know is whether or not this metal ball will float. So we come over here, we have our force of gravity equation, which is simply the mass of whatever you're using times the gravity constant. Our mass, 2 kilograms, times the gravity constant of 9.8 meters per second squared, which equals 19.6 newtons. So then we have to calculate our force buoyant. So we take our volume of 2.5 liters, times it by the density of water, which is 1, and take that times the gravity constant. We get 24.5 newtons. So since our buoyant force is larger than our force of gravity, that means that our metal ball will float. Example number 2. So we have an egg, volume of 56 centimeters cubed, and we place it in a pot of water. The density of an unrotten egg is 1.031 grams per centimeter cubed. Will this float? Now you might be thinking that we'll have to go through that whole process that we did for example number 1, but it's much simpler than that. Since we were given the density of our egg, we can simply compare density of water to the density of our egg. Water's density, as we know from the last problem, is 1 gram per centimeter cubed. Now, does that equal, or is our density of our egg less than? It is not. So, because the density of an egg is greater than that of water, that means that our egg is going to sink to the bottom. Okay, now here we are. We're going to see the real-life application of the buoyant force via the Archimedes principle. Here I have an iron weight plate that says that it's 2.5 pounds. We're going to weigh this out of water with this luggage scale, and then we're going to weigh it in water, having the buoyant force act upon it, and we will then determine the density of it and see if this is truly an iron weight plate or if it's a mixture. Alright, so you take your zeroed out weight scale and you weigh your weight plate. And we see that it is 1.2 kilograms. Now, we take the weight plate off, we zero it out again, and then we weigh it while it is fully submerged in water. And we get a weight of 1.03 kilograms. Alright, now using the Archimedes principle, we can see whether or not the weight plate is actually iron, which has a density of 7.81, or if it's a mixture. So we take the dry weight, which was 1.20 kilograms, and we divide it
by the dry weight minus the submerged weight, which was 1.03. Now, we take that and we plug it into the calculator. And we get a density of 7.05, or 7.06 if you round up. So you can see that the weight plate is most definitely a majority of iron, but it still has something that's less dense mixed in there. This is a real-life application of the Archimedes principle.